Hey, hello. So the question of the day is, does the umbrella in Fortnite hold up to real world physics? Why are we wanting to answer this question? I thought it'd be funny. I thought it'd be fun to do. So I answered the question. To answer the question that we need is ultimately one thing, and that's the required diameter and or radius of a parachute. The equation for the diameter of the parachute is B equals square root 4a over pi. A being the area of the parachute itself. And then to solve for A, we use the equation A equals 2mg over rho v squared. Oh, I'm sorry, I just thought of rho v. All right, let's try that again. 2mg over rho v squared CD being coefficient of drag. M is our mass, our G is gravity, the funny little P is rho is density, and it's the density of the fluid that we're moving through, or density in general. V is velocity, and CD is coefficient of drag, like we already established. So we'll take care of each variable as we hit them, starting with mass. So before we can do that though, we do have to establish a scale to work with. A scale is important because without a standard scale, nothing can work as we won't know the true size of anything. How do we do that? We have to find either a real world object or a known canon height of a character. So luckily in Fortnite, they have a million different characters. So I have Master Chief, so we're gonna use his canon height of 218 centimeters. So we measure him in game. He is 728 pixels in game. And with both of these measurements, we can set up our scale. To do this, we just divide our pixels of 728 by our centimeter height of 218 centimeters. And so we get a ratio of 0.29 centimeters for every 1 pixel measured. Hey, quick editor's note. I said 728 pixels divided by 218 centimeters. That is incorrect. It is 218 centimeters divided by 728 pixels to get the 0.29 centimeters. That is my fault. So back to the video. Thanks for the interruption. Keep in mind that is from the camera distance we're working with, so everything should be roughly the same distance. Now that we have our scale, we can move on to solving for mass. Mass, in this case, is going to be a factor of 3 pieces. Firstly, Master Chief, or our payload. Secondly, the parachute itself, or in this case, the head of the umbrella. And the third part is the shaft of the umbrella, or what Master Chief holds on to. Master Chief's the easiest. We just look up his canon mass of being 451.3 kilograms. Next, we have the umbrella head. The umbrella head is a little more complex. It is using an equation M equals A times TH times rho. A being our surface area of the umbrella. TH is the thickness of the steel itself, and once again, rho being rho, or density. And so, for the surface area, we're going to use this equation. Those funny little p's are called Newton's constant, or at least in this case, because this formula is known as the Knude-Thompson's formula. It's a very rough approximate, it's a very good approximate of an oblate spheroid, which is this fun little picture here. There's oblate and prolate spheroid, but ours umbrella is closest to a oblate spheroid. This is the equation we'll be using, and these are the measurements. A is that first line, B is our second line, and C is obviously that third line going up for height. So with all of these, we'll get our umbrella. So we throw into Photoshop, and we just start measuring our A, B, and C. So with the umbrella, the A and the B are going to be the same, and those give us a measurement of 0.56 meters, and we get a C of 0.16 meters. So now that we have those measurements, we just measure the umbrella itself while we have it in Photoshop, and we get a thickness of the steel of being 6 pixels. So we multiply our 6 pixels by our scale, and then we can get a actual thickness of 0.01 meters. So we plug in our numbers and we get an answer of 2.3896 meters squared. And we'll divide this by 2 because we only have the upper half of our ellipse, or ellipsoid. And so we get a surface area of our umbrella that we are working with of a 1.1948 meters squared. So now that we have the surface area, we can plug it into our mass equation. Our mass equation, we have our area, we have our 6 pixels, which we already converted those 6 pixels for thickness, and all we have left is density. I chose C1020 steel because that's the steel I chose. So we plug in what the density of that steel is, which is 7,850 kilograms per cubic meter. Plugging all those in, we get a nice fun little mass of 168.516 kilograms for the upper part of the umbrella, or the head. The umbrella the umbrella shaft is rather easy. All we need to do is measure the radius and the length and plug it into this website. Hey, one more editor's note. I realize now that in the script I actually wrote it where I skipped over explaining the radius and length. So this little image here, the reason it's doubled up is because the angles are weird, but roughly the length of the shaft is 193 pixels, while the radius is about 8 pixels. So then converting that to what it's supposed to be, we can then plug it into the website. So there we go. Sorry about another interruption. Continue with the video. This website is very helpful as it has many different calculators. And anyway, we plug it in, we get a mass of 2.045 kilograms for the shaft of the umbrella. With all of this, we add our shaft of the umbrella, our head of the umbrella, and Master Chief together to get a total mass of 621.8610363 kilograms. All right, cool. That's per se the hard part done. From here, we'll return to our original equation of area equals 2mg over rho v squared CD. What we have next is gravity. Gravity is not hard to solve. All we have to do is fall off of a tower. So that's exactly what I did. I fell off of a 10-meter tall tower, which took 0.49 seconds when timing it to complete that journey. We plug in our numbers into the gravity equation, which in this case is 2d over t. D is distance, t is time. And we get a gravity of 83.29 meters per second squared. So cool, we have gravity. Now, finally, we have the numerator of our fraction completed. Now for the denominator. The denominator is a much shorter process. Firstly, rho. Rho just requires looking up the average density of air and choosing our number. Depending on where we are, depending on the temperature, the sea level, the density of air changes. But we're going to use a higher number because the higher the number, the more likely that this parachute could actually work. There's more air particles for that actual cone. It's not a cone, for our half hollow ellipsoid umbrella head to interact with, which will allow it to slow down more. So we're going to use the air density number of 1.4545. Secondly, we have v, or velocity. The equation for velocity is distance divided by time. So I fell 100 meters whilst with my umbrella out, timed it out to be 20.11 seconds. So we just divide 100 meters by our time of 20.11, and we get a velocity of 4.97 meters per second. Lastly, we have CD, or coefficient of drag. All we need to do for that is look up the coefficient of drag for different shapes. The reason we're able to do this is because what the coefficient of drag is simply what the general shape's drag property is. So for a square, it has a set coefficient of drag based off that shape. In this case, knowing that our umbrella is closest to the hollow hemisphere, we'll use the coefficient of drag, we'll use the drag coefficient of 1.42. So with this, we have all of the required numbers to complete our adventure. So when everything is plugged in, we get a required area, plugging in our mass, gravity, rho, density, and coefficient of drag, and velocity. Oops, I said rho and density, it was the same thing. Plugging everything in, we get a required area of 2,028.53 meters squared. Plugging that number into our diameter and getting a nice little answer, we get a diameter of 50.82 meters, which gives us a required radius of 25.41 meters. So what do I do with this information? Not much. We can happily know that we have successfully proved a video game wrong. Yay us. A game that was not meant to be realistic is not realistic. Shocker, right? But on the idea of realism, could this umbrella ever work? In theory, yes. If you rearrange the equation, which I have done here, and work backwards, plugging in the numbers that we have from the umbrella, we can get it to work. Because we can up the density of our air, so much that the umbrella is able to descend at the rate seen in game. But what is that required density? It's not good. The required density is 8,899 kilograms per cubic meter, or close-ish to the density of Mercury, which is roughly 13,000 kilograms per cubic meter. It's more than lava, which lava sits around 3,000, but it's less than Mercury. It's not a good time, so congratulations, you will crush your lungs with this pressure pretty much immediately. You'll choke to die. So if you're ever given the option to be put in any video game, don't choose Fortnite, because you would almost immediately die from the extreme gravity and absurd air pressure. But anyway, yay, we proved Fortnite wrong. Epic Games, you're wrong. Anyway, I hope to do more of these. If you guys have any ideas for a game I could screw around with and find some weird math or physics related thing like this, that'd be great. Leave that in the comments. If there's anything I can do better for this, please let me know. Thank you all for watching. Thanks for sticking around with this, and I hope to see you with another episode of Dumb, or whatever I choose to make. Thank you all for watching. Have a great day. Bye.